Hello, my name is Chris Mack, and I'm going to be giving a presentation that I gave about 2 weeks ago at the SPIE Advanced Lithography Symposium. The title of my talk is Modeling Metrology for Calibration of OPC Models. My co-authors are with Mentor Graphics. Ananthan, John, Yunfei, Christian, and Costas did much of the work that I'm going to be presenting here today. I'm going to begin with a little bit of a review of modeling used in OPC, optical proximity correction, and how those modeling efforts have progressed over the years. The basic idea of OPC modeling is that design from a chip comes in one side, and we have a model that predicts the edge positions of all the features on that design. In one sense, the model can be thought of as a black box. It's especially in the early days, was quite empirical in its nature, and it was calibrated based on lots and lots of measurements of edge positions for test patterns. But over time, this black box model has become less empirical, and one way it's done that is by separating out various physical effects. For example, the optics, the projection of an image of a mask into a photoresist, is a well-known physical phenomenon, and people have developed fast ways of modeling this quite.
So we can separate out the optical model from the resist model. That can be carried out even further. For example, the mask can be separate from the optics. So phenomena on the mask like biases between the design and the actual mask, corner rounding on the mask, even 3D mask effects in the slopes of the absorbers can be included in a more physically based model. The advanced separable OPC modeling is twofold. First of all, we can incorporate as much physics as is known and possible for the speed constraints of doing this modeling into our models and making the resulting models less and less empirical and therefore more predictive. We also by separating into various components, we can also improve the modeling by measuring some of the input parameters rather than calibrating those input parameters. For example, in the optics, we can measure the shape of this source for a real system that's being used to print our wafers instead of modeling it. We can measure aberrations. We can measure thin film parameters that are needed in the optics modeling. Other parameters we could measure, but sometimes don't. For example, the mask making biases or corner rounding on the masks. We might measure and input those. Or if we don't, we can calibrate them with known physical constraints. We know reasonable values for how much the mask bias might be based on our experience, and we can use those constraints to guide our calibration as well. What remains the most empirical of all the models that we've separated out in our OPC modeling is the resist model. The reason for this is quite simple. The real world is three-dimensional, but for the purposes of fast simulation, we compress 3 dimensions into 2 dimensions. We do all of our modeling two-dimensionally excuse me, in the resist, and that results in a fair amount of empirical nature to the resist model as compared to some of the other models used in our OPC. A consequence of this evolution of our OPC models to be more physically based, separable into more physically based components, is greater accuracy in our predictability. Well, if we go back to this interface and just think about the most empirical piece so far, the resist model, what comes out of the optics model here is the image in resist. So the image in resist becomes the output of the optics model and the input to our resist model. What we're going to do when calibrating our models is compare a predicted critical dimension coming out of the resist model to a measured critical dimension, usually from a scanning electron microscope, CD-SEM. Well, if we were to continue the trend of separating physical processes into separate models, we could take metrology out of the resist model. An image in resist comes in the resist model,
And what comes out of the resist model is a predicted resist profile. But a metrology tool takes the resist profile and turns it into a scanning electron microscope secondary electron signal called a Linescan, which we then measure with an algorithm to extract a CD. So that's the experimental process. We could put those processes in our model as well, and that's what this work will do today, show us how a metrology model can be separated out from the resist model for more predictive predictions. So let's see how we're going to do that. We're going to do that by first creating what I'll call a virtual CD-SEM using the JMONSEL Monte Carlo simulator. JMONSEL was developed at NIST, mostly by John Villarrubia. It is a rigorous model to describe the scattering of electrons as they enter into a material, the generation of backscattered and forward scattered electrons and secondary electrons, which then can emerge, interact with the sample, and eventually secondary electrons could be detected by a detector. We are going to use this simulator to calibrate a second model. Well, this would be a great model to use in OPC, except for the fact that this Monte Carlo simulator would be a great model to use. It's slow. It can take minutes to hours to simulate one feature, and with OPC modeling, one of the most important constraints is that we have to do things very, very fast because we're doing a very large number of simulations. So instead of using JMONSEL or any Monte Carlo simulator, we're going to use the analytical Linescan model. The analytical Linescan model is a simple equation that can be solved quickly, and we'll calibrate the analytical Linescan model to the Monte Carlo simulation results. That is, JMONSEL will be our virtual SEM. We'll calibrate the ALM to that, and then we'll be able to use the ALM for fast simulations for whatever resist profile we want to measure. I've described the analytical Linescan model in other presentations in the past, so I'll only very briefly describe how it works. If we have a beam of electrons striking the sample, that beam will enter into the sample, and we'll describe the energy distribution as a double Gaussian with a forward scattering width and a back scattering width or range. We'll assume that the secondary electron yield coming out of it is in proportion to this double Gaussian, and then a certain number of escaped secondary electrons will be captured by our detector. Now, as this beam moves close to a feature, these forward scattered and back scattered electrons within the sample begin to interact with the edge. Some of those back scattered and forward scattered electrons might be absorbed by the edge, some might escape, some released electrons coming out of the substrate might be absorbed by the sidewall. Backscattered electrons can in fact strike the sidewall and generate secondaries in the sidewall material itself. All of these can be detected. Likewise, at the top of the feature, we'll get interactions as well. As the beam of electrons near the top, on the top, gets near the edge, we'll get an enhancement of the number of escaped secondary electrons coming out of the edge. It's what we call the edge bloom of a secondary electron Linescan signal. So we put all of these effects together. They're all physically based, and we'll come up with an empirical model that is inspired by the physics of what's really happening. And this is the equation that comes out. It looks a little bit scary, but believe me, the fact that you have an analytical equation is much nicer than Monte Carlo-based kinds of simulations. There are 11 physically based parameters for the Linescan coming from an isolated step. One of those is the probe beam width, a Gaussian beam of electrons incident upon the sample, and the other are all beam material interaction parameters. They depend on the voltage, but also on the material properties of the substrate and the feature. This has been extended to interacting edges as well to create features with some extra parameters associated with that. And if I have a step that has a sidewall angle, then the value of some of these parameters changes as a function of sidewall angle as well. This is all previously reported in other papers that I've done, so I'm not going into a whole lot of detail here. Here's an example of an output of both the Monte Carlo simulation and the analytical line scan model. So in the blue, we have a little bit of a squiggly blue line. That's the Monte Carlo simulation with a large number of electrons simulated so that there's very, very little noise in my simulation. And then in the red, I have the analytical line scan model result. Now, this is not the best fit of the ALM to this line scan. If I were to create the best fit of the ALM to this line scan, it would fit perfectly. You would see virtually no difference whatsoever between the blue and the red curves. What I've done here is fit the analytical line scan model over all ranges of feature sizes and pitches and heights of the resist and sidewall angles, and created one generic model that handles all of those cases. And then here's the example of how this one overall analytical line scan model matches one particular line scan. And you see it's not quite as perfect because I'm not adjusting the parameters for this specific case, but I get this kind of predictive ability over a wide range of features. One thing we've done new in this study is looked at resist features, which are modeled as PMMA, on top of a thick layer of organic BARC, which I also model as PMMA in terms of its material properties. All right, so now I've got an analytical line scan model that does a good job of matching the Monte Carlo simulations over a wide range of resist sizes and shapes. Then we're going to extract a CD value by using a simple threshold model. We'll pick a threshold level between a baseline and the max intensity, and we'll measure the width of that feature at that threshold level. Now, algorithms on CD-SEMs often use a threshold-like algorithm, but there's a lot more complication involved because there's noise in the scanning electron microscope, secondary electron signals, and there's a lot of filtering and noise suppression that goes on in order to extract a stable threshold value. We don't have to worry about that with the ALM because it's an analytical expression without any noise whatsoever. So we just do a simple threshold extraction of the CD. Now, in order to predict what the CD value will be, the input to the ALM is a trapezoidal description of the 3D resist profile. So we use Metrographics compact 3D resist model. This has been described in other publications, so I won't go into details, but it predicts resist profiles, which, for example, in this shape, include the entire shape of the resist profile that we might want to measure. What we do with this profile is fit it to a trapezoid, because the input to the ALM is a trapezoidal shape. It can handle asymmetric shapes like this one I pictured here, although in our case all of the features that we're going to be modeling are in fact symmetrical. We're going to take the middle 60% of the sidewall and fit a straight line through it, and then the bottom will be the bottom CD. We'll take the resist height to be the height exactly at the middle of the profile. We didn't observe any footing in our simulated cases here, and while top corner rounding was predicted, we ignored that in this study. We're going to include top corner rounding in a subsequent study. So we fit a best fit trapezoid to the simulated 3D resist profile, and that became the input to our analytical line scan model. So let's talk about how OPC models are calibrated. We begin by defining a set of training patterns which we make into a photomask, and then this mask is printed onto a wafer with the nominal process. We might also vary dose and focus, as we did in this particular experiment, and we measure those training patterns on a CD-SEM. We use those data values to calibrate our model, and the model would include, for example, all of the resist parameters and possibly some mass parameters like biases, etc. We can separate out some number of these patterns, training patterns, and use them as validation patterns. These are patterns that we would not use to calibrate our model. Instead, they would be included on the test mask, printed on this wafer, and measured, but we would compare the model output to the validation patterns after we calibrate with completely different patterns. And this gives us a way of validating how predictive the model will be. And the RMS difference between the measured validation patterns and the predicted validation patterns with the model is a different measure of the quality of the model than, say, the RMS value of the calibration results. So here's our experiment. We had a 22 nanometer node metal layer process with a set of 1D mask features. In fact, 221 mask patterns of different dimensions and pitches were used. We measured them at best focus and best exposure dose, but also some of those patterns we measured through focus and dose for a total of 728 measurements. Each one of these measurements we call a gauge, that is a different unique value of mass pattern, dose, and focus. They're all 1D patterns. They were all measured on a 500 volt CD-SEM for the metrology. We then took these 728 gauges and we randomly split the data in half. In fact, we took the in-focus best dose, 221 mass patterns, and split those in half. And then we took all the out-of-focus or off-dose cases and split those data randomly in half as well. We used 1/2 of all the data for calibration purposes, and the second half was reserved for validation of the best calibrated result. The two metrics that come out of this exercise are the calibration RMS difference of the experiment from the simulation and the validation RMS difference between the experiment and the simulation. Now, since we can randomly split the data in half in lots of different ways, we repeated this multiple times, again with different random splits of these mass patterns, and we did it 25 times. For each of these, we get a calibration and a validation RMS difference, and the average of all of those results we'll use to compare simulations with and without the ALM. So we'll run this entire exercise using the plan of record, the normal metrographics model and approach for calibrating that model. And then we'll do the same thing but with the ALM added into the modeling. Here's the results. Now, let me mention something important here. The ALM has a large number of parameters which we calibrated against the JMONSEL virtual SEM at the very beginning of the work. At this point, we made no adjustments whatsoever to any of the ALM parameters. We didn't let them float. We didn't try to calibrate the ALM whatsoever. The only parameter we measured was the threshold value used to extract the CD. We varied that from 0.3 to 0.7, and for each one of those cases, we looked at the average percent difference. This is actually the fractional difference, not the percent. So 0.05 would be 5% difference. A positive value means that the use of the ALM produced a 5% better RMS difference compared to not using the ALM. Typical calibration RMS values were about 1.2 nanometers, and typical validation RMS values were about 2.5 nanometers. So what do we see? Well, we see that for almost all of the cases, the validation RMS value is in the 4 or 5 or about 6% improvement range. The calibration, a little bit different. Sometimes the calibration RMS is better with the use of the ALM and sometimes not. But in almost all cases, the validation RMS values were improved. The one case where it's not is this threshold value of 0.7. But that's actually pretty easy to explain if we just look at one of these Linescan results. If I pick a threshold value, I'm extracting the CD and the outside edges here and here. If I change the threshold, it's like I'm moving this. Excuse me. If I change the threshold, it's like I'm moving this up and down. Well, if I move the threshold too high for any feature that has a sidewall angle, I start reaching this plateau region that is a function of the sidewall angle. And once that happens, my CD value becomes highly unstable. Very slight changes in the feature results in large changes in this CD value. And that's what's happening down here at the threshold value of 0.7. I kind of reach this unstable measurement regime. And so as long as we avoid that unstable measurement regime, we get this, about 5% improvement in the predictive accuracy of our model with the use of the ALM. So what can we conclude from this study? Well, the ALM provides a small improvement. Now 5% is nothing to sneeze at, but it's not a large amount considering the RMS values were 2.5 nanometers. This is a reasonably small improvement. Now this indicates that our current empirical resist models are doing a fairly good job of accounting for almost all the CD-SEM metrology effects, the biases that are in the data. However, I think there's still a lot of value in separating the metrology from the resist models, making this, even if it's small, making a predictive improvement. This threshold level was the only adjustable parameter. It matters a little bit, but as long as we keep it in a stable regime, it doesn't matter that much. Excuse me. Some future work. We plan to extend our metrology to 2D patterns, not just sticking with the 1D patterns we've done so far. We can easily add top corner rounding, and we will do that in a future study. And then we'd like to look at more data sets as well as the one data set we've looked here to validate these results even further. Well, that's my presentation. I would like, however, at the end to acknowledge Ben Bundy of SUNY Poly-Semitech. He ran all the JMONSEL simulations of resist on BARC that we used to calibrate the ALM, and then using that calibrated ALM in our study here. So thank you very much, Ben, for all of your hard work. And thank you.